the concavity and the second derivative test, the points of inflection, the extrema and second derivative test, and some optimization problems related to the business and economy. About the concavity, the meaning of the concavity is to have the graph having that form, concave upward, which we call it concave upward, and if it's concave downward, it will have the positive slopes around, but with an increase in the slope decrease, and in the concave upward we will have positive slopes as well with an increase in the slope. So these are more forms for the concavity. If it's concave upward, it will be looking like this. I can memorize this with the happy face. If it's concave upward, it may also called convex or convex downwards, but we will always use the expression of the concavity in order not to mix them up for simplicity. And here is another form of the concave upward. That's another form of being concave upward. The orange concavity is downward, so we may memorize this by the sad face. If you imagined eyes here, so it will be a sad face, and it might be called, just for your information, convex upwards. And we need to know also the points of inflection where the function got different concavity around it. So if we have a negative concavity or concave downward, not negative, downward concavity, followed by upward concavity, we will call this point in between is the inflection point. So if we have a concave down followed by concave up, it will be an inflection. And if we have the inverse concave up followed by concave downward, it will be an inflection as well. And this is the third form for an inflection point. If you remember, these were the points that we called in the first derivative test neither nor, where the function got increase before and increase after. But now we know that we have two different types of increase with the concavity. The increase before the third point is with concave upwards, and the increase after this point, the third one, is the concave downward. So again, here is the inflection point with different graphs. They define that concavity is where we can get points or join point to another point without crossing the curve. If this happens, if we have a point joined to another point in the same interval without crossing the curve like it happened here, these 2 points crossed the curve and these 2 points crossed the curve. This is in the definition of the concavity, just for more accuracy of the definition. And we might remember the concave upwards as well with the cup. And how can we do it? We will use the derivatives like we did in the last worksheet. So our general power rule is to drop the power and subtract 1, recalling the derivatives. If we have a constant function or if we have a number, its slope or its derivative is 0. If we have a times x, it will be only the number, which we called it the slope as well. Let's go to the worksheet and examine some of these problems. Taking part C, our steps will be like we did with the with worksheet 6. First, we will find the first derivative, which is here we have a quotient or a division. We might work as in the division rule, or we might take the denominator upwards with the power -1 and do the product rule. So let's derive this inflection point using the quotient rule. We will take the denominator as it is, power of 2, and then we copy it upwards without derivative, times derivative of the numerator, which is u here. Derivative of 4 is 0, so all this term is cancelled, minus 4 times the derivative of the denominator, or the v, which is 2x. And therefore we can simplify this, that we have in the numerator negative 8x in total divided by the same quotient. Now we will derive the second derivative, because the inflection points and the concavity works in the second derivative, works with the second derivative. Let's derive the second derivative, where we have again here u over v, so we will take the v squared. Now the v is squared, so we are going to square it again, and then copy it upwards in the numerator without derivative as it is, with the power of 2, and then times derivative of the numerator. Derivative of u is negative 8 minus the negative 8x as it is, and we might multiply the negative with the negative of the rule to be positive 8x, times derivative the v, which is the denominator, where we will drop the power, the outside power, and copy the bracket as it is with its new power, which is 1, times derivative what's inside, which is 2x. Now we can rewrite this and reformulate it algebraically. One might notice that one way of simplifying this is that we have here that bracket, okay, and we have the same bracket in the denominator, and moreover we have it here as well. So in the numerators, with this addition that divides the numerator, we might take that x power 2 plus 3 as a common factor from the numerator, and we will be left with the negative 8. We have taken that bracket, so we are left with another 1 because it was raised to the power of 2 here, right? So we've taken 1, and negative 8 will be left with 1 bracket, plus we have taken that bracket, so we are left with the 8 times 2 times 2 times x squared, so that's 32x squared. And now in the denominator we have this bracket raised to the power of 4. We might now simplify this out. I just want to give you this note. It would help you in the algebra of simplifying that. And we might distribute the negative 8 here inside, because now we are left with that squared bracket in the numerator. So we will have the negative 8x squared, and then the minus 24, and then the plus 32x squared, right? And in the denominator we are going to have the x power 2 plus 3 raised to the power of 3 now. And we might still further simplify this in order to combine the negative 8x squared plus 32x squared in the numerator to get 24x squared minus 24 over the same bracket. Now that's the simplified second derivative, which we will use in finding the inflection points and the concavity. We need to solve it like we did with the relative extrema, where we said that f dash is going to be either in one line where we will equate it by 0, or we are going to have it in a fraction form where we will equate both the numerator and the denominator. And in few cases we found that sometimes the denominator includes a square root, where it will add another points where the f dash would be undefined. Now we will do the same thing with the second derivative. We will accept these two phases as well. So let's solve. The f double dash is equal to 0, and this is where we are going to take the numerator and equate it by 0. And of course this 24 will go to the other side, and we will be left with x power 2 equals 1, which means that x is positive and negative 1. And then we will solve the f double dash where it's undefined, where we will take denominator and equate it by 0. We can take it without the power because we know that when it's equal to 0, this power can be cancelled with taking the third root, and the third root of the 0 is 0. And we found that the denominator can't be equal to 0, so there is no x values generated from the f double dash undefined, because any x will be substituted here. It won't give us the 0 in the denominator. So now we are left with these critical points, the 1 and -1. We will know about the inflection through the second derivative. So let's make our line and indicate the second derivative, our number line that works from -infinity up till infinity. Now it's divided at -1 and at 1. And what we are going to test is these intervals. We have n+1 intervals, so we will test the intervals from -infinity to -1, and from -1 to 1, and finally from 1 to infinity. And where we are going to test in the second derivative. Let's pick a point here. It can be -2, and we will commute the f double dash at the -2 and find the sign, and we will pick a point here. It can be 0, and we substitute it in the f double prime of 0 and find the sign. Here, if we substituted 0, it will be negative, right? And if we substituted -2, it's going to be positive. And finally, let's pick a point here. It can be 2, and the f double dash of 2 is going to be positive. So we have here a positive interval, a negative, and a positive interval. And if the f second derivative is positive, this means that the function got a positive concavity, a positive or upward concavity. If the f double dash is negative, this means that we have a negative concavity, and again the positive is upward concavity. Finally, we need to know that these points are included in the function in order to know their type, whether we would accept them as an inflection point or not. But let's first indicate that the first interval from -infinity to -1, now it's concave. What? It's concave upward, and from -1 to 1, it's concave downwards, and finally from 1 to infinity, it's concave upwards. Right? So these are the interval of concave upward or downward. Now we will pick the points. We need to know the inflection point where there is a change of concavity around it. Like we said here, if we have a negative or a downward concavity followed by upward concavity, this is going to indicate an inflection point. And actually that's the case that we have here. We have different concavity in between the two critical points that we worked on. We need just to double check that the points exist in the function. So we are going to get f of -1 and f of 1. F of -1 is going to be 1, and f of 1 we return to the function itself, which is 4 over the 1 squared plus the 3, and this is equal to 1 as well. So the function is defined in the both points, yes. Therefore, we will conclude that then at x equals -1 and at x equal 1, we have an inflection point. So not only the change of concavity around the point indicates an inflection point, also it must belong to the domain of the function. Now we have indicated what was required, which is the interval of concavity and the inflection points that we found. Simply what we did was deriving the second derivative from the first derivative, and then we did the same what we did in the last worksheet with the second derivative, with equating it by 0 or undefined. These are the situations where we will drive the inflection points, or the points that we suspect to be inflection points, and then we do our test. Let's do this again with another exercise. Let's do it with part B. So now we have different f of x. Let's do the same and find the intervals of concavity, like it's required here in the worksheet. Find all intervals where f is concave upward or downward, and find the inflection points of f. Now we will directly get the first derivative of x, which is here for 8 is 0, negative 6x, it's negative 6, and then minus 2x, and then followed by the second derivative, which will be negative 2. Oh, now here the second derivative is negative. And we know when the second derivative is negative, this indicates what? Concave downwards. And we don't have critical points, or we don't have points of changing the behavior. We don't have an x in the second derivative. So we will say that this function is concave downwards everywhere. There is no division for the number line. We will not divide the number line into intervals. The whole number line, throughout the whole number line, this function is concave downwards. And we know this function, of course, that's the quadratic with the coefficient of x power 2. Remember when we studied the quadratic earlier, we know that according to the coefficient of a of x squared, if that a is positive, this means that we have an upward concave quadratic or parabola, and when a is negative, the concavity is downwards, where we have a downward concave parabola. So simply this function was a quadratic which is concave downwards. It got no inflection points, and it got one interval throughout the number line where it was concave downwards. Let's take part A. So in part A here, we will get the first derivative. Again, to find it here, 12x squared, dropping the power, and then subtracting 1 minus the 4. This is the first derivative. Driving the second derivative of x, we will get 2 times 12. So that's 24x. Now we can equate this by 0. So we will equate the x double dash by 0, where we will find the 24x equals 0. Solving it for x, it will be 0. Now let's do our test using the second derivative in the number line. We will divide the number line into 2 intervals around 0. Let's test before the 0 with a negative 1 and after the 0 with a 1. We tested what again in the second derivative. So from negative infinity to 0, we can test the negative 1, picking the negative 1 and evaluating the second derivative at negative 1. Here we have 24 times negative 1, which will be negative. And again, testing the interval from 0 to infinity in the second derivative, we will pick the point 1. And 24 times 1, that's positive. So we have here a positive interval and a negative interval. We know when the second derivative is negative, this means concave downward or sad. When it's positive, this means concave upward or happy. So now we have change of concavity around the point that we got, which is 0. This is not enough to indicate a point of inflection, right? But we now at least know that from negative infinity to 0, this function is doing what? It's concave upwards, downwards, right? And from 0 to infinity, this function is concave upwards. Now we know the interval of concavity. Let's test for the inflection. We finally need to know that f of 0 exists, right? In order to call it an inflection point for this function, let's get back to the function and evaluate it at 0. We will find that it's equal to 0, which is a well-defined number, and therefore the point 0 and 0, this is the x and the y coordinate, is an inflection point. So we decide that it's an inflection point because it suffers a change of concavity around it. In addition, the function is defined there, and finally the theorem says that it's derived from the f double dash equals 0. So to cut it short, we will say that there is a change of concavity around it and it exists in the function, or it belongs to the domain of the function. Very well. Let's move to number D. Here we have this type of function. Let's check the inflection point. If we are going to check the inflection point and concavity, therefore we are going to work in the second derivative. So let's derive the first derivative. Here we might of course rewrite this function algebraically because we know how to expand the power of 2. So we might say that it's x and expand the power of 2, the first squared, 2 times the first times the second, so it's going to be minus 12x, and then the last squared, negative x times negative x, which is positive x squared, and then we distribute the x outside inside in order to have x to the power of 3, and then let's organize it, minus 12x squared, and finally plus 36x. Now we need to derive the first derivative, which will be directly 3x squared minus, drop the 2 beside the 12, 24x plus the 36. That's the first derivative. One might not like to do the algebraic or not notice it. You might do the product rule here, taking the u as x and the v is the bracket squared, and go with the product rule, of course. Let's get the second derivative, where we will have for the first term, again we have 6x and then minus 24, that's the second derivative, where we will go to solve it equals to 0. So if we have 6x minus 24 equals 0, this means that x is equal to 24, which is x equals 4. So we will go to the number line and divide the number line around the 4, where we will get this form from negative infinity to infinity. And test using any point before the 4 in that interval from negative infinity to 4. We might pick here the 0, and then test in the second derivative, where we will get a negative value. So this interval is negative, which means a negative concavity, a downward concavity. And after the 4, let's pick 5. And substituting the 5 here will make it positive interval, which indicates an upward concavity. So now we know the intervals of concavity. We know that this function from negative infinity to 4 is concave downwards, while from 4 to infinity it's concave upwards. And for the inflection point of 4, we need to test the function first. Let's test the f of 4. So pick the put the 4 here. 6 minus 4 is 2 squared, which is 4 times 4 is 16. So it's a well-defined number, and therefore this is our inflection point. right? Okay. Now we need to make the best benefit from that second derivative that we learned about finding the points of inflection and the concavity of a function. We knew that if the second derivative is positive, this means that we have a concave downward, a concave upward if it's positive, and if it's the second derivative is negative, we have concave downward. And concave downward means that we have what? That we had for the relative extrema types. We have a relative maximum point, right? And if the second derivative was positive, which means an upward concavity, this means that we had a relative minimum point. And this is where we drive, or we might find a second way to find the relative extrema that we found out using the first derivative test in worksheet 6, using now the second derivative. So we will say that if we have a concave upward, this means that we have a relative minimum, and this were derived from getting the second derivative what? Positive. And if the second derivative is negative, this means that the function is concave downwards and it got a relative maximum or a maximum peak. And this is the inflection point again, where we have a downward concavity followed by upward concavity. It doesn't have to be having peaks around. So this is the point of inflection. Okay, so let's go here with the second derivative test to find all relative extrema or the local extrema of the functions, the relative maximum and the relative minimum, using the second derivative test. Let's start with part B. Now we will use the second derivative test in order to drive the relative extrema again. For part B, let's get the f dash of x, which is the 3x squared minus 12, and then for getting the relative extrema, the critical points, we equate the first derivative with the 0 and we solve it. So we will get the x squared equals 12 divided by 3, which is 4. So it means that x is the positive and negative square root of 4, which is positive and negative 2. Very well. What we will do now using the second derivative test is that we are going to get the second derivative, which is here 3 times 2, 6x. And then we will substitute the critical points we got from the above step, the f double dash at 2 and the f double dash at negative 2. The second derivative at 2 is going to be 6 times 2, which is positive. And if it's positive, it means that the concave is upward and we have a relative minimum point, right? And if the second derivative at negative 2, it's going to be negative 12, which is equal to a negative number, and hence the concavity is what? Downwards, and we have a relative maximum. So you might say that this is the not direct test. If it's positive, we expect its maximum, no, it's minimum. If it's negative, then it's maximum. And remember the concavity behind that. So now we have an alternative way to find the relative maximum and the relative minimum using the second derivative test, but this test got a drawback, a strong drawback, where it sometimes fails. So let's say when would that fail? It would fail if simply the f double dash became equals to 0 at the critical point where we got if it's equal to 0, the second derivative is unable to indicate the type of the critical point, and if it was undefined. At another critical point, if we find it undefined, so again it's going to fail to indicate the type of the critical point. Let's get more exercises in that part. For part C, now we will directly get the first derivative, which is from here. We have a product rule, and here can we combine this algebraically? If 9 minus x are raised to the power of half, which is the equivalent power of the square root, we can't distribute the x, of course. So let's apply the product rule, where we have the first as it is, the u, times the derivative of the second, the derivative of v, where we will drop the power, and then the new power will be half minus 1, which is negative half, times the derivative of what's inside the bracket, which is negative 1, plus, this is the product rule, the root of 9 minus x as it is, times the derivative of u, which is 1. Now we find that we have a negative bracket in the derivative. So let's organize this algebraically. In the numerator, we have negative 1 and x, right? So we have negative x in the numerator. In the denominator, we have the 2, and this bracket, which is raised to a negative power, it means that it was in the denominator. So we will move it to the denominator with the positive power, plus the square root of 9 minus x. Now we have a fraction plus a linear or one function in a line, and we said that we have to combine these two when we get this situation. So let's combine it. We imagine that this one line is over 1, and we get a common denominator, and then multiply this one with the negative x to get negative x, and then the plus will move here, and then we have this times that, the root times the root, so we will be canceling the root out, and it will be 2 times 9 minus x. Let's simplify this f dash finally, where we will have here negative x, right? And then 2 times 9, which is 18, 2 times negative x, which is negative 2x. So we have negative x minus 2x. We will have 9 minus 3x over the 2 times 9 minus x under the root, which is the power of half. Now we have f dash as one fraction, so we might solve it. First, if f dash is equal, f dash of x is equal to 0, this means that we have 9 minus 3x equals 0, and then 9 equals 3x, so x is equal to 3. And then we have here f dash is undefined, and we usually take the denominator and equate it by 0. So if we took the denominator here as it is and equate it by 0 at the beginning, we will find that we will divide by 2 both sides, right? We will be left with the 9 minus x to the power of half equals 0, and then get rid of the square root with squaring. We will get 9 minus x equals 0, and finally we will get x equals 9. And we will notice that we have a square root in the denominator, which means that not only the 9 that will make this function undefined. If we have a root, we said that the negative inside the root, or the input, if it's negative, this means that we will get an error or the function is undefined. And hence we know that if 9 minus x was less than 0, was negative, this means that f dash is undefined. So f dash is undefined not only at x equals 9, but when x is, let's solve this, when we take this to the other side, so it's going to be when x is bigger than 9. Take the negative x with the other with the opposite sign, with the opened interval, with the opened inequality. So when x is bigger than 9, under the root we will get a negative number where this function won't be existing. We might do this incomplete if we need to know the points that we will solve. So we might take the intersection of that interval with the domain of the function itself. So the domain of f here, you remember the domain, the first topic we discussed, where the 9, our condition here will be that 9 minus x be bigger than or equal to 0 in order to keep it positive, right? Which means that x is what? Take negative x to the other side with the closed inequality, which means that x is less than or equal to 9. The intersection of these two inequalities is giving us the 9 that we got with equating the denominator by 0. So now we have the critical points x equals 3 and x equals 9. Using the second derivative test, remember, now we will get the second derivative and then use it for our test. The second derivative is, this is the simplest form we got for the first derivative, so let's use it to drive the second derivative. We have here a u and v, u upstairs and v downwards. So let's take the denominator as it is, raised to the power of 2, and then we copy it in the numerator without derivative, and then find the derivative of the numerator. 9 derivative is 0 minus 3x, so we get times negative 3 minus the numerator as it is times derivative the denominator, where we have 2 times half. The 2 will cancel out the half, so we will drop the bracket with the new power, which is half minus 1. Now it's negative half, and then times derivative what's inside. Derivative of 9 is 0 and negative x is negative 1. We might change the sign of the rule to positive in order to multiply it with the negative, right? Now we have 9 minus 3x and times 9 minus x, which is raised to the power of half. What we are asked to do now is simply to direct substitute. So we don't have to spend time in simplifying this form of second derivative. Let's directly substitute with the 3 first that we got, and then with the 9. Now substituting with the 6. Okay, let's correct this here when we're substituting or simplifying the f dash. In distribution of the 2, it was 2 times 9, which is 18. And then solving the f dash equals 0, it's 18 minus 3x, driving x equals 6. So testing the second derivative at 6, we will get a negative number, which means that we have a relative what? A relative maximum. Now substitute the 9 in the second derivative, and whatever the sign is, we know that here. So here, substituting the 9 in the second derivative, notice in the denominator we have 9 minus x, so it's going to be 9 minus 9 in the denominator, so we will get an undefined value. And we said that if the second derivative gets an undefined value, this means that we have a failure for the second derivative test, so we will say that it fails or it can't indicate the type of the point. Now, if the question was indicating to use the second derivative test and it failed, which means that the second derivative is equal to 0 or undefined at the given point or at the point that we generated, we will say that simply it fails. But if the question says that you got to find the relative extrema and you were choosing to use the second derivative test and it fails, you got to make the first derivative test for only that point. So in real world, when we get more complicated equations and we get bigger number of critical points, we use the second derivative test to know quickly the type of the point of as much points as we can, And then where the second derivative test fails, we go and make the first derivative test. It will be done, it's a lot of calculations, yes, but it will be done for a few number of points then. So for the 9, we can make this first derivative test and test before and after in the first derivative, before and after 9, and we will get the type of its peak. Let's have a look over the shape of that function. This is how this function looks, the x times the square root of 9 minus x. It seems that at x equals 6 here, this is the 5 and that's the 6. So at x equals 6, we have a relative maximum peak, really. And at the 9 here, we will find that the derivative is going to be crossing the x-axis, so we won't have a peak. So even if we use the first derivative before and after the 9, we will find that the function is decreasing. So it will get a negative before and a negative after, and therefore it will be a neither nor type, because it does exist in the function. If we found f of 9 finally, we will find that it's corresponding to 0. So 9 minus 9 here is 0, 0 times 9 is 0. So f of 9 is 0, which means that it's well defined in the function. And if it has a decreasing before and after, so it's a neither nor. Its relative or its critical type as a critical point is the neither nor type. So this function got a relative maximum only at x equals 6. And this is what the derivatives analysis told us. So now we can use this for any function which we are unable to graph or is very complicated to go with. So we might do this analysis and know everything about the function or what we indicated now using the first derivative and the second derivative. Here in exercise B, we got x power 3 minus 12x, and therefore we will get the first derivative, which is 3x squared minus 12, and then equated by 0. This is the second step. 3x squared minus 12 equals 0. It means that x squared is equal to 4, and therefore x is equal to 2 or negative 2. These are our suspected critical points. Using the second derivative test, we will derive the second derivative from the first here, 6x, and then we'll substitute that as a third step at 2 and at negative 2. Substituting it at 2, we got a positive, which means a relative minimum. And if we get a negative, it means that we got a relative maximum. We might be asked for that value at the relative minimum, where it happens at x equal 2. That value would be how much? And we might go to calculate it using the corresponding y, like we know using the f of x. So that's the minimum, the relative minimum value that this function might reach at x equals 2. And this is the relative maximum value, 16, which the function might reach at x equals negative 2. Let's have a look over the graph of this function, x power 3 minus 12x. So this is how it looks. We might minimize it. Yes. So here we have a peak at this point on the curve where it's 2 and negative 16, and we have a maximum peak where it's negative 2 and 16. So the function is increasing before the negative 2 and decreasing from negative 2 to 2, and from 2 to infinity the function is increasing. Very well. Now we are done with the first two exercises. Let's go to the optimization problems, where we are going to maximize a profit, minimize a cost, or maximize a revenue. This is what's meant by optimization, where we are required to find the intervals of increase or decrease, or the relative maximum, relative minimum, or maximize a value, minimize a value, like tuning, like you're tuning the channels in order to reach the required channel. Here we are tuning the quantities that we have in the economy and finance in order to maximize or minimize. Let's first recall before starting this our formulas that we used before, where we know that the profit is the revenue minus cost, right? We know also that the revenue is the X times price. We sometimes call the price or that P the price or the demand. X as well, we call it the quantity of production, right? Or the production level. It's the same thing when we say the quantity of the production. And we got the average cost, which was the total cost divided by X. We also got the word marginal, and marginal means the rate of change or the derivative simply. So this is the derivative of something. Now let's get to that problem. The profit P made by a cinema from selling X bags of popcorn can be modeled by this model, and we are given the model, which is usually a simple model like this, where X varies from 0 to 50,000. Find the intervals on which P is increasing and decreasing. We need to know when this function would increase and when it would decrease. And of course, we got to know this using the first derivative like we did before. So we will get the first derivative, which will be what? 2.36 minus 1 over 25,000 times the 2x, right? And we shall equate that by 0, where we will get an x value with the 29,500. Now we need to test the function around this value, where we will divide the number line. Now if x varies from 0 to 50,000, so from 0 to 29,500, which we got as a critical point, we will test the p dash and we will get a point in between. We might use, for example, 1 or any value in that interval at x equal 1. So the p dash of 1 turned to be positive or was greater than 0, which indicates that p was increasing. And then pick any point in the interval from 29,500 up till the maximum x that we got. Of course, you might do that mathematically. You might divide the number line from negative infinity to the 29,500 and from 29,500 to infinity. This would be correct as well, but mathematically. But here, according to the context of the problem, it was given that the x varies from 0 to 50,000, so it's of no use to use it from negative infinity to infinity. We are only interested in that interval or in that entire domain of the function. And now we will test any point in that interval. Let's pick, for example, 30,000. And we will find that p dash is going to be negative, where it indicates that the function is decreasing. And therefore, we know that p would be increasing from the interval 0 to that point, and from this point to the maximum x, it's going to be decreasing. And this was the requirement in part A. In part B, it says, if you owned the cinema, what price would you charge to obtain a maximum profit of popcorn? If you owned the cinema, you need to set the maximum price for the popcorn. Let's recall what was x here. X was what? X was the bags of popcorn, so it's the number of bags, right? And what we know about the profit is that it's the revenue. Let's take that exercise. To discuss part B. Here, so we know that the profit is the revenue minus cost, right? And we are given the profit problem here. So we need to obtain the maximum profit. So as if we need to maximize the profit, in general. Okay, in general, how many bags would we sell if X is the number of bags and we need to maximize the profit? So we need to know the maximum profit at which value of X. We will say that we need to know the maximum profit at selling at the position where we sell the maximum number of bags that we can sell, right? That would definitely get the maximum profit. So at X equal 50,000, we need to maximize the profit at that in X value. We know when we try to get the intervals of increase and decrease for that given profit, where if we compared it to what we know about the profit, that it's the revenue minus cost, it becomes here this value minus that one minus the 3,500. So we might say that it looks like the 2.36x minus this part plus that value, right? And what we know that it's the revenue is that the revenue, which is X times P minus the total cost which we have collected here in this bracket, can be compared to the profit that we are given. And hence we might conclude that the price was the coefficient of X in the given profit, which is $2.36. This was the price for the bag, the maximum price that we can set for the bag in order to obtain the maximum profit, but at which X? At the X that we derived, so at the X equals 29,500 that we picked in part A, right? Because this is what we got from working in that function. Now we need to know what would be the price to obtain the maximum profit that we can set for the bag, but at a different value of X. So as if we're having the same profit, but with an unknown cost. We might call it P, small p, like we know, times X, okay, minus the same rest of the problem, or rest of the given formula for the profit. And then we need to do exactly the same thing in order to maximize it. We are going to derive its first derivative in order to know its increase and decrease, and any constant times X derivative is the constant minus the 2x like we did before. Divide that number, and the derivative of the 3,400 is 0. Now we have to get this at X equals, or first let me say that, so we usually equate the P dash by 0 like we do, and moreover we know that the X that we need to maximize at is the 50,000, so we will equate it by 0 and at the same time substitute the X with the 50,000. So the price is going to be the 2 times the given X divided by the 25,000, and hence we will find the price $4. So this is the maximum price that we can set per bag if we are selling the 50,000 number of bags. Okay, let's move to exercise 4. In this exercise, you are given the total cost of producing X units. Find the production level. We said that the production level is denoting the X value, right? So here we are required to find the production level that minimizes the average cost. And what we are given is different forms of the total cost. Let's do part C. And of course, it's recalling us that the average cost per unit is the total cost divided by the number of units. This formula which we used to use. Now, if we need, what I want you to pay attention to is that we need here to minimize which value? The average cost, right? So we need to find first the average cost equation that models the average cost. So let's take the average cost. We are given the total cost, and we know that it's the total cost divided by x. So we have here 2x squared plus 5x plus 18, all of this divided by x. So we have here 2x plus 5 and then plus 18 over x. And then we do like we do, we get the first derivative. Derivative of 2x is 2 and 5 is 0, so it's cancelled, plus 18 times 1 over x. We used to rewrite this as x to the power of -1, and then the new power would be -2. We might write it directly, and we know the shortcut is that the derivative of 1 over x is -1 over x squared, and then we equate this by 0 in order to find the x value. We know if we have a fraction and a number, we might combine this into one fraction in order to get the correct critical points, all of the critical points required, and hence we will get here 2x squared minus 18 like we did before. Let's equate the numerator with the 0, and then we will be having x squared equals 18 divided by 2, which is 9, which means that we have x is positive or negative 3, and equating the denominator by 0, where f dash is undefined, and we will get that x is equal to 0. And of course now we know that x is here is representing the number of units produced. So if the number, imagine that we have a factory that produces negative quantity. Of course here the -3 and the 0 both are rejected because of the context of the problem, and because x here is locating the number of units produced, or we can say simply the production level, the number of produced units, right? Yeah, so we are left with x equal 3. This is the value where we can test, and of course also one might notice that we need to minimize the average cost, so we will test the average cost, and instead of making the first derivative, also for example here, we might drive the second derivative simply and test the type of this point with the second derivative. So let's get the second derivative of the average cost. The 2 derivative is 0 and minus 18 x to the power of -2. This means that we will drop the 18 times 2, and the new power is -2 minus 1, which is -3, right? And then we can substitute this 3 in order to get a positive value, which means that at x equal 3, we have a relative minimum value, because when the second derivative is positive, this means concave upward, which means a relative minimum value. And at x equals 3 is a minimum value, so this is where the average cost will be minimized. If we needed to get the production level, the requirement was to find the production level where it minimized the average cost. So now we know that it's at x equal 3, right? There is an extra part here in part C, show that the marginal cost, remember that the marginal cost was the C dash, or the dc by dx, the derivative, right? So we might get derivative from the given total cost here. Before continuing this, we have 4x plus 5, right? That's the derivative of the total cost. We need to show that the marginal cost that we write now and the average cost which we had here, the average cost which we the C bar, it was the 2x plus 5 plus the 18 over x. They are equal at this minimized average cost. So it means that it's equal at the same production level, which is x equal 3. So at x equal 3, if we substitute x equal 3 here, we will get 17. And here as well, 3 times 4, 12 plus 5 is 17. So they are equal at this production level. And here we go. Let's move to exercise 5, where it says the retailer has determined that the cost for ordering and sorting X units of a product to be modeled, whatever the context or the details is, in general we have the model for the total cost and its working domain. The delivery truck can bring at most 200 units per order, and this was told here. Find the order size that will minimize the cost. The requirement here is to minimize the cost, hence, and we will be working in the model of the cost or in the cost equation. So we will drive, let's move to exercise 5. We will drive here the derivative of the total cost, which was given here, yes. And the derivative of 3 is 3x is 3, and this plus 1 over x times 20,000. The 20,000 is constant. We might separate them. So we'll say that it's negative 1 over x squared, and then we put it in one fraction, equate the numerator alone with the 0, which will drive this value, and equate the denominator alone with the 0, which will get x equals 0. And again here we have the x, which was representing the units of a product to be modeled. So it's the number of units for a product. If the factory is producing negative quantity, of course this is not accepted in real world. So we will reject the negative value and also the 0. If the factory is producing 0, so there is no production and there is no economy, or there is nothing. So we rejected as well here. So we are only left with the positive critical point that we drive, which is the square root of 20,000 by 3, which is approximately 81.65, simply as x got to be bigger than 0. We consider now the 81 and the 82 as the critical points. We can't do that rounding mathematically, that it's going to be 82, because this 6 after the decimal is greater than 5, so we will round this up. This is mathematically, yes, but according to the economy or the financial point of view of that application, we need to consider the 81 and the 82, and hence we will evaluate the cost at these two quantities that we picked, and we will get the one which minimized the cost, which is got the least value, which is 489.9. Okay, so here we will pick the 82. So at x equals 82, this cost will be minimized. And here in the solution, it calculated the cost at 200, which is the maximum amount of our number of units. It's something extra which wasn't required of the problem. In exercise 6 here, we are asked to find the commodity. A commodity has a demand function modeled by the small p, and we know the small p is denoting the demand or the price, right? So that is the given price, and a total cost function is modeled by that function. What price yields a maximum profit? Now we need to maximize the profit, so we need first to generate the profit. We know that the profit is the revenue minus cost, right? So let's take this to discuss it in a better way. So because we need here to maximize the profit, and we know that the profit is the revenue minus cost, we are given the cost, okay, and we are given the price or the demand, and we know that the demand is related to the profit, to the revenue. The revenue is the demand times the production level. So we will simply say it's x times that 100 minus 0.5 x power 2. So the revenue is 100x minus the 0.5 times x power what? Power 3. That's the revenue. And we are given the cost, and hence we can say that the profit is simply that form. It's the revenue, which we calculated, 100x minus 0.5x cubed, minus the cost, which is 40x minus 37.5. And of course, we would combine the like terms. So 100x will be combined with the 40x to be 60x. The 0.5 doesn't have a like, so it will be dropped. And also 37.5 is dropped because it doesn't have a like term. Now we have this total modeling the profit. We can go to maximum to get the maximum, or maximizing the profit by finding the first derivative and then equating it by 0, right? And we will be left with these x values. Solving this equation equals 0. And of course the negative is rejected because the x here is representing the number of units sold by this commodity. So we will get the x equals square root of 40. This is the x that we would consider. And then in order to get the maximum profit, we need to show that at this x value that we accepted, the square root 40, this is where the profit is maximum. So we need to do this using either the first derivative test or the second derivative test. So if the second derivative test is easily derived, we might find the second derivative from that part. We will get the second derivative, drop the 2 in order to get the negative 3x. This is the second derivative. And then we substitute the point, the critical point, square root of 40 to find the negative value, and negative value indicates a maximum relative. And a maximum relative is where the profit will be maximized. So at x equal, because again the square root of 40 is between 6 and 7, so we will test the 6 and 7 and obtain the maximum. The maximum profit will be obtained at 6, not 7. So we will pick the x equal 6, and we will not do the rounding mathematically. So at x equals 6, this is the production level that would yield a maximum profit. And the price at this production level, we can go to the demand equation and directly substitute this amount, number of units, 6, in the price or the demand equation to get it $82 per unit. In the second requirement, it says when the profit is maximized, this is where we pick at x equals 6, what's the average cost per unit? Now we are given the total cost, where we can generate the average cost with dividing that total cost by x. So we know that the average cost is the total by x. So we divide every term by x because it's a common denominator, and algebraically we know that we can distribute the common denominator upon the terms in the numerator, and then simply substitute x by 6 to find it as 46.25. In exercise 7, we have a company that has determined that its total revenue in dollars for a product X can be modeled by this equation, where X is the number of units produced and sold, what production level, which means what X value will yield a maximum revenue. And we need here to maximize the revenue. Therefore, working in the revenue model, we will get the first derivative first, like we do, and then we equate it by 0 to generate the x values. And we have here 3 x values because this derivative got x to the power of 3, so we have 3 values. The 0, of course, is rejected, and if we got a negative x value, also we rejected. We get these two positive values, and we need to know which of them would maximize the revenue. So we have either to use the first derivative test or the second. Here, to drive the second derivative is easy, so we might go and get the second derivative from that first, negative 12x squared plus 2240x minus 24,000. And then we directly substitute the two values that we got, the 256.6 and the 23.4, and we get the negative. The negative means that it's a relative maximum, and we need it here to maximize the revenue. The negative means that we have a maximum, and the positive, the second derivative, when it's positive, means that we have a minimum value, and therefore the minimum here in the second point is rejected because this is a relative minimum, and the question says we need to maximize the revenue or get the production level, the x, which would yield a maximum revenue. So we will pick the 25.6, and in order to get the accurate number of units, because it can't be decimal, of course, the number of units, we would examine the 25.6 and the 25.7 in the revenue model and pick which would maximize the revenue. So here we have 1.18 to 1.182, but here 1, so we would pick this point which slightly maximize the revenue rather than the 256. These are very interesting problems in the core of your specialization. The company estimates that the total cost in dollars of producing X units of a product can be modeled by this model. So that is the total cost. Find the production level, which means find the X that minimizes the average cost. So it seems that we need to commute the average cost from the given total cost. So we know that the average cost is C by X. We will divide every term here by X to generate the average cost, and then we go minimize it or see when it's going to be minimum. So we get the first derivative and equated by 0. The first derivative is simply driven and equated by 0 to get the positive and negative 2000. And because again the X here is representing a production level, we would reject the negative, going with the positive. We might get the second derivative in order to indicate the type of the peak at the 2000. So the derivative is 1600 by x to the power of 3. If we substituted x by 2000, which is positive, the power of 3 would keep it positive. So it means when the second derivative is positive, there is a minimum. So this is a relative minimum point, or where this function would get a minimum peak. So at x equal 2000, this is the production level where the average cost is minimized, or that minimizes the average cost. That was our discussion for worksheet 7. I hope you do well in the quiz. See you next time. Thank you for your attention and goodbye.